Have you ever felt a shock when touching a metal door handle after walking on a carpet? That little jolt comes from electric charges building up, and to understand how those charges move and interact, we need to explore a fundamental concept: electrostatic potential. Electrostatic potential at a point is defined as the work done in bringing a unit positive charge from a point far away, called infinity, to that location without letting the charge accelerate. Think of it like slowly pulling a tiny test charge closer to another stationary charge you're doing work against the electric field. The formula for electrostatic potential is V equals W divided by Q. That's V, the potential, equals W, the work done, divided by Q, the charge. Now, here's something cool. Electrostatic potential is a scalar quantity. That means it has magnitude but no direction. Also, it can be positive or negative depending on the nature of the source charge. For a positive source charge, the potential is positive. For a negative source charge, the potential is negative. Let's now move to the equatorial line, that is, a line perpendicular to the dipole axis and passing through its center. Let's place our observation point P somewhere along this line, at a distance r from the center. Since the distances from both charges are equal, and since one charge is positive and the other negative, their individual potentials cancel out. So what do we get? V equals V plus plus V minus, which becomes plus kq over r minus kq over r, which equals 0. Yes. On the equatorial line, the electric potential is exactly 0. This is due to perfect symmetry. The scalar potentials are equal and opposite, and they cancel each other out. But in most real-world cases, your observation point won't be strictly on the axis or on the equator. So what if the point is somewhere else, at a distance r from the center and making an angle theta with the dipole axis? In that case, we use the general formula for dipole potential. V of r equals 1 divided by 4 pi epsilon naught multiplied by p cosine theta divided by r squared. Let's break this down. V of r is the potential at point r, p is the magnitude of the dipole moment, which is q times 2a. Cosine theta is the cosine of the angle between the dipole moment vector and the position vector, and r is the distance from the center of the dipole to the point. This formula tells us the potential depends both on angle and distance. When theta is 0 degrees, that is, you're on the axial line, cosine theta is 1, and you get maximum positive or negative potential. But when theta is 90 degrees, on the equatorial line, cosine theta becomes 0, and so does the potential. So the formula naturally captures both special cases. Now let's discuss how this dipole potential behaves. First, unlike a point charge where the potential falls as 1 over r, here it falls faster, specifically as 1 over r squared. That means, at large distances, the dipole's influence fades more quickly. Second, the sign of the potential depends on the side of the dipole you're on. That's because one side is dominated by the positive charge and the other by the negative charge. Third, the equipotential surfaces, which are the imaginary surfaces where the potential is the same, are not perfect spheres. They bend and curve around the dipole in complex shapes. This is why dipoles are excellent models for molecules, antennas, and even atomic structures. They produce fascinating, non-uniform fields and potentials. Let's solve a numerical example. A dipole has a moment P equals 3 into 10 raised to the power minus 29 coulomb meter. We need to find the potential at a point located 0.1 meters from the center along the axial line. We'll use V equals 1 divided by 4 pi epsilon naught multiplied by P cosine theta divided by r squared. Given P equals 3 into 10 to the power minus 29, r equals 0.1 meters, theta equals 0 degrees, so cosine theta equals 1, and 1 by 4 pi epsilon naught is approximately 9 into 10 to the power 9. Plugging in values, v equals 9 into 10 to the power 9 multiplied by 3 into 10 to the power minus 29 divided by open bracket 0.1 close bracket squared, which is 0.01. That gives us 27 into 10 to the power minus 20 divided by 0.01, which becomes 2.7 into 10 to the power minus 17 volts. So, the potential at that point is 2.7 times 10 to the power minus 17 volts, very small but significant at atomic scales. Alright, let's formalize what we just discussed using a bit of math. Suppose you have n-point charges, which we label as Q1, Q2, all the way up to Qn. Each is located at position vectors r1, r2, through Rn. Now, the potential at some observation point P due to one single charge, say Qi, is given by Vi equals 1 by 4 pi epsilon naught multiplied by Qi divided by Ri. Since potential is a scalar, we apply the superposition principle directly. So the total potential at point P becomes V equals summation from I equals 1 to n of Vi, which is V equals 1 by 4 pi epsilon naught multiplied by summation of Qi over Ri. What's beautiful about this is, it doesn't matter where those charges are placed in space or whether they are positive or negative, you simply plug in the distances and signs and sum the results. Let's take a special case, a classic configuration known as a dipole. Suppose you have two charges, plus Q and minus Q, placed symmetrically along the x-axis, separated by a distance of 2a. Now we want to calculate the electric potential at a point P that lies somewhere in space. Using the same superposition idea, the potential at point P is V equals 1 by 4 pi epsilon naught multiplied by open bracket Q divided by R plus minus Q divided by R minus close bracket. Here, R plus is the distance from point P to the positive charge and R minus is the distance from point P to the negative charge. Now, if point P is very far from the dipole, meaning the distance R is much greater than A, we can apply binomial approximation. The expression simplifies to V approximately equals 1 by 4 pi epsilon naught multiplied by P cosine theta divided by R squared, where P is the dipole moment given by Q times 2a. And theta is the angle between the dipole axis and the position vector. So what we see here is that a dipole is just a special case of a system of two charges and it obeys the same rules, just with some elegant simplifications. Let's now visualize what this all means in terms of space. When you have a single charge, the equipotential surfaces are spheres centered around the charge. But in a system of charges, especially more than one, these surfaces bend, twist, and stretch. Why? Because each charge is pulling or pushing on the potential field in its own way. These surfaces are where the potential value remains constant, so if a test charge moves along them, no work is done. Understanding these surfaces is not just theory. They help us predict how electric fields behave in complex situations, such as inside capacitors, molecular dipoles, and even around neurons in the brain. As you'll see in the diagram, these equipotentials for two opposite charges look like banana-shaped loops, distorted by the push and pull of both charges. Let's solve an advanced level example to tie this all together. Here's the problem. Three charges are placed at the corners of an equilateral triangle of side 1 meter. Q1 equals plus 3 microcoulombs, Q2 equals minus 2 microcoulombs, and Q3 equals plus 1 microcoulomb. We are to calculate the net electric potential at the centroid of the triangle. Step 1. In an equilateral triangle, The distance from each vertex to the centroid is R equals 0.577 meters. Step 2. Use the formula for each potential. Vi equals 1 by 4 pi epsilon naught multiplied by Qi divided by R. Now plug in the values. V equals 9 into 10 to the power 9 multiplied by open bracket 3 minus 2 plus 1 close bracket times 10 to the power minus 6 divided by 0.577. That simplifies to V equals 9 into 10 to the power 9 multiplied by 2 into 10 to the power minus 6 divided by 0.577. The answer comes out to be approximately 31,200 volts or 31.2 kilovolts. So, the total potential at the centroid due to this triangular system of charges is 31.2 kilovolts. Different charge arrangements create different shapes of equipotential surfaces. For example, a single point charge, say a positive charge, produces spherical equipotential surfaces around it. All points at the same distance from the charge have the same potential. And when you place two large, parallel metal plates with opposite charges, the field between them is uniform. Here, the equipotential surfaces look like flat sheets stacked like pages in a book. Let's recall the potential due to a point charge. It's given by V equals 1 divided by 4 pi epsilon naught multiplied by Q over R. That's V is equal to 1, 4 times pi times epsilon times QR. This equation helps us understand why the surfaces are spherical. Potential depends only on distance R from the charge. And the closer the equipotential surfaces are to each other, the stronger the electric field in that region. That's why in diagrams, the denser the surfaces, the more intense the field. Let's go deeper into the behavior of these surfaces. One key point: electric field lines always intersect equipotential surfaces at right angles. Why? Because there's no component of the electric field along the surface. Now, can two equipotential surfaces intersect? The answer is no, and here's why. If they did, that single point would have two different potentials, which is impossible. Remember, the electric field always points from higher to lower potential, and the steepest descent happens perpendicularly to equipotentials. We also know that the work done in moving a charge from point A to point B is W is equal to Q multiplied by VA minus VB. But on an equipotential surface, VA equals VB, so work done is 0. Let's now connect this to real life. Imagine you're looking at a contour map of a hill. Each line represents the same height. That's the same as an equipotential surface in electrostatics. Just replace altitude with electric potential. In electrical systems, metal conductors, like wires or aircraft bodies, are often equipotential surfaces. Any excess charge distributes itself in such a way that the entire surface is at the same potential. A powerful example: the metallic body of an aircraft acts as an equipotential during flight. Even during a lightning strike, the charge spreads instantly, keeping passengers safe. And in capacitors, each plate is an equipotential surface, maintaining uniform voltage across its entire surface. So, equipotential surfaces are not just abstract physics, they are engineered into real-world systems. Let's solve a numerical to strengthen our understanding. Problem: a test charge of 2 microcoulombs is moved along an equipotential surface around a point charge. The displacement is 5 centimeters. How much work is done? Let's solve this step by step. Step 1. Recall the work formula: W equals Q into delta V. That's W equals Q times delta V. Step 2. Since we are moving along an equipotential surface, delta V is 0. So, W equals to microcoulombs times 0 volts equals 0 joules. Answer: no work is done when moving a charge along an equipotential surface no matter how long the path is. This reinforces our understanding. It's the potential difference, not distance, that determines the work done. Now, imagine you're building a configuration of charges, one particle at a time, starting from infinity where they don't interact. Every time you bring a charge closer, you're doing work, either adding energy or letting it release, depending on attraction or repulsion. So, the potential energy of a system is essentially the total work done in assembling it. For example, for multiple charges placed at fixed distances, the total potential energy is calculated by summing over each pair. We write this as U total equals the sum over all I and j of 1 by 4 pi epsilon naught multiplied by qi into qj divided by rij, where rij is the distance between the ith and jth charge. This idea becomes really useful when we study systems like molecules, crystals, or capacitors. Let's simplify it down to just two charges, say Q1 and Q2, placed at a distance r. Their potential energy is given by U equals 1 by 4 pi epsilon naught into Q1 times Q2 divided by r. Now here's the key insight. If Q1 and Q2 are both positive or both negative, the product is positive, so U is positive. That means you're storing energy while assembling. But if one is positive and the other negative, the energy becomes negative. That's nature helping you. Energy is being released as they pull each other closer. It's like lowering a weight. Gravitational energy becomes negative as it moves toward Earth. Similarly, electric potential energy reduces when opposite charges come closer. Now, what if we take three charges, say Q1, Q2, and Q3, and place them at the corners of a triangle? To calculate the total energy stored, we consider every unique pair and their interaction. So the total potential energy becomes U equals 1 by 4 pi epsilon naught multiplied by open bracket Q1 into Q2 over R12 plus Q2 into Q3 over R23 plus Q3 into Q1 over R31 close bracket. Here R12, R23 and R31 are the distances between each pair. As you can see in the diagram, we have a triangle showing the three charges and the distances labeled between each. This pairwise method is simple yet powerful, and it forms the basis for calculating energy in much larger systems. So, how do we handle n charges in a system? It's just an extension of the same idea. You calculate the potential energy between each unique pair and add them all up. The formula becomes U equals the double summation over I and j greater than I of 1 by 4 pi epsilon naught into qi into qj divided by rij. Why double summation? Because we want to ensure that each pair is considered only once. This is especially useful in physics and chemistry, where multiple charges interact in a molecule, crystal lattice, or capacitor plate. It allows us to calculate how much energy is inherently stored in that configuration. Let's apply what we've learned through a numerical example. Three charges, each of 1 microcoulomb, are placed at the vertices of an equilateral triangle of side 0.1 meters. We are to find the total potential energy of this system. Step 1. First, calculate energy between any one pair using U pair equals 1 by 4 pi epsilon naught multiplied by q squared divided by a. Putting in the values, U pair equals 9 into 10 to the power 9 multiplied by 1 into 10 to the power minus 6 squared divided by 0.1. This gives us 0.09 joules. Since the triangle has three sides, there are three such pairs. So, total energy, U total equals 3 into 0.09 equals 0.27 joules. And if you check the visual, the triangle diagram shows all three charges and equal side lengths.
That's the end of the part.
One of the topic electric potential and capacitance. See you folks on the next lecture. Have a great day and happy lean ring.